We are now recording. Class is now in session. Hello, everybody. Okay, let's talk about some business. Before we go over the answers to the last quiz, let's talk about some business. On Wednesday's class, right after I cut off the recording, then somebody asked a very important question, which led to a discussion which did not get recorded. So let me make sure that I say it now so that everybody can hear it, even the people who aren't here live. Okay. We decided during our conversation after the Wednesday class to change the schedule for the test because there's an AP test on Friday, and I didn't want you guys to have to take both classes the same days, even though technically we probably could have squeezed them in. Just not a good idea. And Thursday didn't work out because there was a chemistry test. So the plan now is that on Monday, not this coming Monday, but the Monday after that, May 18th, that's when we're going to have the final test for this class. And it will not be a comprehensive test. It'll only cover the stuff that we've learned since the last test. So quantum mechanics and relativity. So here's what I've decided I'm going to do next week. You can see it on the screen right here. So we're going to go on Monday. We're going to go over the answers to tonight's homework. And yes, I'm sorry, but I am going to have to give you some homework tonight. Things got compressed. Mr. Wilson came out with a directive saying that today was the last day that we could introduce any new material. And so some stuff that I was going to do next week, I had to squeeze it in. So there is going to be some homework tonight. Sorry, but you know the other Fridays I've let you off, right? Okay, so Monday we'll go over the answers to the practice test, or the answers to tonight's homework, and that's when I will give out the practice test. On Wednesday we'll spend the whole day, the whole class period, going over the answers to the practice test. So Friday is the day that I was going to give the test, but that's been moved back. So I'm not going to be holding class on Friday. If you have questions, just email them to me. If I get enough people asking me for help, it's possible like I could schedule a help session on Friday from 1 until 2. I could do that, but only if I get enough people asking for it. So I'm not planning to do that, but I am open to that possibility. And then Monday's the test. Okay, and so during that same week, the week of the 18th, that's when you need to be returning textbooks. And you should have received an email, or if you haven't got it yet, you should be getting one very, very soon from Mr. Wilson and Mr. Katoa, telling you how we will be setting things up so that you can come into the school, drop off the textbooks without hopefully violating the social distance regulations. Okay, so are there any questions about what I've just gone over? Okay, I don't see any, so I'll go ahead and move on. Okay, so let's talk about the answers to the quiz last time. Okay, so we know that for a person on the spaceship who's moving at 97% speed of light, 10 years has gone by for them. So we want to know how much time is going to pass for the person on Earth. Now, having taught this for several years, I know that many of you are saying, well, I know that there's this factor that Mr. Hendricks likes to call gamma. And by the way, it's not just me, it's physics books call it that. So I know that I'm going to have to calculate what gamma is. So I'm going to take v, square it, divided by c squared, and then do the square root of 1 minus v squared over c squared. That's what's going to be gamma. And so you're saying to yourself, well, I know that to convert from one to the other, I either need to multiply by gamma or I need to divide by gamma. How do I remember which one it is? Okay, so here's the way I do it. Okay, I look at this picture, at least in my mind, and I say, so if the person who's on Earth, if they were to measure various quantities about this spaceship that's going zipping by them, okay, this is what's going to happen. The person on Earth is going to measure the spaceship as having more mass than it would if it was at rest. They're going to measure the clock as ticking more slowly than it would if it was at rest. And if they measure the length of the spaceship, they're going to measure that the length of the spaceship is shorter than it would be if it was at rest. So keep this in mind, and from this you can derive everything else. All right, so for our situation right now with question number 1 on the quiz, we know how much time has passed for the person on the spaceship. And we know that the person on Earth is going to say, well, that time is less than the time on Earth. Okay, so if I give you the time on the spaceship, then do we multiply by gamma or do we divide by gamma? Okay, and remember that gamma is always less than 1. Okay, so if we take the time on the spaceship, if we multiply it by gamma, and gamma is less than 1, that's going to give us a smaller number. So we know, well, that can't be right. So then we know it must be the other one. We know that what we're going to have to do is we're going to have to divide. You take the time on the spaceship, divide it by gamma, and that'll tell us how much time went by on Earth. See, so that's the way I approach all of these questions, all of these types of problems, and I recommend that you do the same. Okay, so the first thing is calculate gamma, and remember, when I give it to you as 97% of the speed of light, don't get out your calculator and type in 0.97 times 3 times 10 to the 8th. Don't do that. Leave it as 0.97c, because that way when you put it in the equation, you're going to have a c squared on top and a c squared on bottom, and they're going to cancel out. So then all you need to really for gamma then is 1 minus 0.97 squared. All right, so now we know what gamma is, and we know that we need to divide, so bingo, we get the answer. Okay, if you approach all of these that way, it's going to be very easy. All right, so question number 2. Okay, this time we're asking about the length of something. Okay, and again, gamma, it's the same gamma. Doesn't matter if it's time or mass or length, gamma's the deciding thing. Okay, so we calculate gamma, and then we ask ourselves, okay, do we multiply by gamma or do we divide by gamma? So we go back to this same picture here. We say, okay, well, the person on Earth is going to measure the spaceship as being shorter. Okay, so if I know what it is on Earth and I want to know what it is when it's passing by, okay, so I need to take the number I have and I need to come up with a number that's smaller than that. So that means I need to multiply by gamma, not divide by gamma. You see how this works? It's actually pretty simple. Okay, so I calculate what gamma is, I multiply by gamma, and we're done. All right, now the last one is talking about mass, but this time I didn't tell you what the speed was, but I did tell you what the mass was. And you hopefully already know what the rest mass is for an electron. Okay, that's a number that you should have done so many homework problems by now that you have that one memorized. Okay, but if not, you at least have it written on your cheat sheet. Okay, so we know the mass of the electron when it's at rest. We know the higher mass that it has when it's moving. So all we have to do is figure out, okay, which one is which. So we know moving one has more mass. Okay, so we could go with either way. Either one of these equations would work, you know, because I've given you both the masses. So we take either one of these equations, I don't care which, and rearrange it to solve for gamma. And then that'll tell us what we want. Okay, so if we rearrange it, we solve for gamma, we find out what gamma is. And then we take the equation up here for gamma, and we manipulate it until we find out what is the velocity relative to c, and works out to be 0.94 times c. So relativity problems are actually quite easy. Understanding relativity can be a little weird. The implications of relativity can be a little weird, but the mathematics of relativity turns out to be pretty easy. Okay, so everybody good with that? Not seeing any questions. So I'm going to assume that no news is good news. And let's move on. Okay, so the twin paradox. This was the question that I left you with last time. Many people think the fact that the moving twin is younger than the twin back on Earth, they call that the twin paradox. If you go onto Google and you Google the phrase twin paradox, what you'll get is, the talk about the fact that the moving twin ages less than the stationary twin. That is not a paradox. That is something that's totally understandable if you think of quantum mechanics and how it relates to relativity. Okay, the fact that your body is not a little particle, or let's say the electrons and protons that make up your body, they are not little marbles floating in an empty space. They are fluctuations in the fabric of the universe. You are intimately tied to the fabric of the universe. You are part of the fabric of the universe, inseparable. So if you get pushed through the fabric of the universe at high speed, it's not surprising at all that that's going to put some stress on your molecules. It's going to cause them to vibrate more slowly. So your clock's going to run more slowly, your body's going to age more slowly, your brain is going to think more slowly. Nothing paradoxical about that. The paradox comes when you've got the two twins, and so the one twin thinks the other twin is aging more slowly, but the second twin says, no, it's the first twin that's aging more slowly. And I claim that they're both right. That is the paradox. Okay, so let's talk about that more. Let's see if we can resolve the paradox. So the twins that we're going to pick on today are going to be Alejandro and Francisco. Okay, so one of these, let's say the one on top is Alejandro. Francisco seems to have a little bit more common sense than Alejandro does. Francisco has figured out that spaceships work better if you stay inside them. Alejandro, for some reason, hasn't figured that out yet. Okay, so anyway, okay, so if you were to ask Alejandro who's moving, Alejandro would say, well, hey, I'm at rest, and Francisco's the one that's moving. But Francisco's going to say, no, 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 I'm the one that's at rest, you're the one that's moving. Okay, all right, and the first postulate of relativity is it's impossible to say who's right. So we have to do the mathematics assuming that they're both right. Even though we know that one of them, we know one of them is clearly moving. There's no question one of them is moving. The question is which one. And Einstein says it really doesn't matter which one. Okay, you can do the math either way, and you'll get the right answer as long as you do the math properly. Okay, so what we're going to do is we're going to have Francisco and Alejandro. They're going to synchronize their clocks when the two of them are right next to each other. Okay, so they set their clocks so they read exactly the same amount of time. And then we wait a little while. So now Alejandro. Alejandro is the one who thinks that he's at rest. So if we were to ask him a little bit later, he would say, well, Francisco has moved over here. Therefore, since Francisco is the one that's moving, then less time will have passed on his clock. Okay? But Francisco is going to say, no, 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 I'm the one that's at rest, you're the one that's moving, therefore less time has passed on your clock. Okay. Now I'm claiming that they're both right, and so hence the paradox. How can they both be right? Well, here is the answer. Okay. The answer is that the question is what's wrong. Okay. According to relativity, if you have two different people at two different places in the universe, you can't compare clocks. It's meaningless to try to compare clocks. The only way that you can compare clocks meaningfully is if they're both in the same spot. Okay, so what's happened now is that we got Francisco over here, or I'm sorry, that one's Alejandro. Alejandro's over here, Francisco's over here, and we want to compare their clocks, but they're not in the same spot. So what we need to do is we need to get them back together. And then and only then we can compare the clocks. So there's two ways we could get them back together. One way is to have Francisco turn his spaceship around, fire up his rockets, and go until he meets Alejandro. Okay, now Francisco is going to think he's at rest, so he's going to say, okay, no problem, I'll just start moving. Now Alejandro is saying, well, you were already moving anyway, and so it doesn't matter. He was moving this way. Now we're going to turn around. But here's the important thing: in order for Francisco to catch up with Alejandro, Francisco is going to have to travel faster than Alejandro traveled. Therefore, when they get back together, neither one of them is going to be surprised to find that Francisco's clock is going to show that less time has passed. Okay? Even Francisco, the one who thought he was at rest at the beginning, and he thought that Alejandro was the one that was moving, he will not be surprised because he realizes that in order to catch up with Alejandro, he had to travel faster than Alejandro was traveling. So neither twin is surprised to find that Francisco's clock shows less time has passed. Now, what if we were to do it the other way around? What if Alejandro is the one that fires up his? Well, the exact same argument applies. When they get back together again, Alejandro is going to be the one who has less time showing on his clock. And neither one of them is going to be surprised by that. Okay? So you see that the question of whose clock shows less time doesn't have meaning unless we can figure out a way to get the two of them back together again. Okay? So that is the answer to the twin paradox. I hope you guys are good with that. I haven't seen anybody type anything for a long time. That always has me worried. Can somebody just give me a thumbs up, thumbs down? I know it sounds weird, but okay, so I see a smile. Okay, oh, and more smiles. Okay, good. All right, okay, good. I'm glad to see that you guys are at least awake. Okay, so let's move on now. The secret word, okay, already we got that. Let's not worry about that. Okay, so here are the answers to last night's homework. So I'll give you a few minutes to look those, or I'll give you a little bit of time to look those over. Okay, so the first postulate of relativity, this is really important. I left this for you to read from the handout. Remember, it's not my job to read the handout to you. Okay, so the first postulate of relativity is that it's impossible to say who's moving and who's at rest. And in fact, it doesn't matter who's moving and who's at rest. As long as you do the math properly, you'll get the right answers. And then the second postulate of relativity is that everybody in the universe is going to measure the speed of light as being the same value, regardless of whether they're moving or not. And this kind of follows from the first postulate because everybody in the universe thinks they're at rest, right? Okay, and then the rest of the questions, there's the answers. Are there any questions? Okay, not seeing any. I'm seeing the word no. Okay, all right, good. So this relativity that we've been talking about here, the special relativity, the mathematics of it is really easy, and if you think about it, conceptually, it's not as bad as you might first appear. Okay, so what we did last night was called special relativity because it's just a special case of the more general type of relativity. And by the way, that's what tonight's homework is going to be about. And that's what today's class is going to be about, is we're going to talk about the more general form of relativity. Okay, so basically relativity is all the weird stuff that happens, the time dilation and all the other fun stuff like that. All the weirdness that happens because of this. Special relativity is just a special subset. Special relativity is the weirdness that happens because you're moving at high speed. But it turns out that weirdness happens even when you're not moving at high speed. And so that stuff is what we call general relativity. And general relativity, really, it all results from the same thing. It results from the fact that mass is not what we thought it was, and matter is not what we thought it was. We used to think that matter was a little ball floating in an empty space. Now we know that empty space isn't empty. We know that there's a fabric there. And we know that mass is not even a little ball. What mass really is it's a distortion in the fabric of the universe, a ripple, if you will, in the fabric of the universe. So let's talk about that a little bit more. Here's a picture that I have shown many times, and I don't really like this picture. I'm going to show you in a second another picture that I like better, but let's start with this picture. A lot of people, they have in their mind the fact that they cannot get it out of their mind that mass is a little ball. And so a lot of people think that mass causes the fabric of the universe to be stretched. Very, very common misconception. But that's wrong. It's backwards. Okay? mass does not cause the fabric of the universe to be stretched. Mass is what happens when you stretch the fabric of the universe. If you take the fabric of the universe and you grab a hold of a little bit of it and you stretch it a little bit and then you let go, it'll spring back. So grab it again and stretch it a little bit more. Let go of it, springs back, okay? But if you can stretch it enough, and when I say enough, I mean like E equals mc squared kind of enough, okay? If you can figure out a way to stretch the fabric of the universe to where you exceed the E equals mc squared limit, okay, then something happens that causes it so that when you let go, the fabric of the universe stays locked in that stretched state. And scientists don't really understand why it stays locked into that state. They've come up with a lot of different theories, and the most promising one right now is something called the Higgs boson that I'm sure that a lot of you guys have heard about. And in fact, in the Large Hadron Collider on the border between France and Switzerland, they have recently discovered, they have observed this thing that they call the Higgs boson. And unfortunately, we don't have time to talk about bosons and leptons and all the really cool stuff, you know, quarks and string theory, things that I had intended to talk to you about. But because of this darn coronavirus, we're getting cheated. Actually, you guys are getting cheated. So we're not going to be able to talk about bosons and leptons and all that fun stuff. But there is something that happens where when you stretch the fabric of the universe enough, a Higgs boson somehow gets involved, and the fabric of the universe will stay stretched when you let go of it. But even then, you have to be careful, because if you flick it hard enough, then what can happen is that you'll unlock it, and then it'll snap back together again. And when I say flick it hard enough, I mean like inside an atomic bomb. Okay, in order to get the atomic bomb to go off, you have to have a very massive explosion that provides enough energy to get it past the threshold to where you get the Higgs boson out of there. Okay, and then all that stretched fabric then becomes unlocked, and boom, it goes back into being unstretched. And what happens is you get a tremendous wave going out of energy as it radiates outward from the place where the mass used to be. Okay, so keep this in mind. Mass does not cause the fabric of the universe to be stretched. Mass is the stretch in the fabric of the universe. Okay, so with this in mind, let's think about some strange things that might happen now that we know this. Okay, so we start with E equals mc squared, which we've already talked about. Okay, so I don't really need to say any more about this. Okay, but so that tells how much energy is stored in that stretched fabric of the universe. So that's one of the weird things that happens as a result of general relativity, is that you can change from matter to energy, back to matter, back to energy. You can do that. Okay. Another of the strange things of general relativity is portrayed in many movies, but the best and most recent one is this movie right here, Interstellar. So, okay, good. I see at least one of you has seen the movie. How about the rest of you? What do you think? So give me some yays or nays. All right, so Josh did not see it. Hiram did see it. Any no? Oh, looks about half and half. Okay, so about half of you have seen the movie, about half of you have not. Oh, Cohen thinks that it's the best space movie ever. I agree it's a good one, but I like 2001 Space Odyssey better myself, but let's not go there. Okay, so it looks like about half of you have seen the movie and half of you haven't. So I'll need to tell you a little bit, basically what's happening. Well, at least the part that's relevant to this discussion is that the astronauts, they go to a place where the place they're visiting has way more mass than Earth, and even more mass than the sun. Okay, basically what you see here is a black hole. Okay, so they're in the vicinity of this black hole. They're really close to this black hole. Okay, and those of you that have seen the movie, you know that what happens to them is time slows down. Um, so the reason it slows down is fully understandable if you think about it in terms of quantum mechanics, exactly the same way that we did for special relativity. The argument that I give for why time slows down in the case of special relativity is that your body, which is part of the fabric of the universe, whether you like it or not, okay, when you push your body through the fabric of the universe at high speed, it creates stress, which causes the molecules to vibrate more slowly, therefore you age more slowly. Well, the exact same thing is happening if you are here. So here we have a highly massive object. And I wish those little balls weren't there, but all of the pictures that I was able to find on the internet, they always show the ball being there. So, okay. All right, so here we have a region where the fabric of the universe is stretched really tightly because it's near a very massive object. And so that tightness is going to cause stress that is going to behave very, very similar to the stress that would occur if you were moving quickly. So it's not at all surprising to find that the clock in this highly stressed region is going to tick more slowly than a clock that's out here where the fabric of the universe is not stressed. Not surprising at all if you think about it this way. Okay. All right. So time slows down, or we could call it time dilation if we want. And in fact, there is even an equation that will tell you how much the time slows down. Now, I'm not going to derive this equation, so please forgive me, okay? So I'm just going to throw it out there. Now, I'm hoping that many of you are going to react by saying, well, hey, Mr. Hendricks, if you don't derive that equation, then I refuse to believe it. If that's your reaction, then my response is good for you. Glad to hear that, okay? So treat it as a suggestion, okay? Seeing as how I haven't proven it. But a lot of work has been done by scientists, and experiments have been done where they have in fact verified that this is true. You guys know in your phone you have a GPS, right? So if you activate the GPS, your phone knows exactly where it is, and it tells you turn by turn, directions. If you want to go visit somebody's house that you've never been to, your phone communicates with some satellites up in space, and so based on that, it knows where it is, and then you can figure out where to turn to get to your friend's house. Those satellites, the GPS satellites in outer space, the way they work is they have a little clock inside of them. It's one of those atomic clocks like I talked about last time. Remember how I said they took 4 atomic clocks? 2 of them they put on an airplane, flew it around the world. The other 2 they kept in the lab. And when they got them back together again, the ones that were in the airplane, less time had gone by for them. Okay. Well, the clocks that are in those satellites are the exact same kind of atomic clocks. They are super, super, super accurate, and they need to be. And so I don't want to go into all the details of how the GPS works, but basically, if those clocks in those satellites are not accurate to a phenomenal degree, I mean, 1/100th of a second, not good enough. 1/1000th of a second, not good enough. Okay, it's got to be way more accurate than that. And so what scientists have discovered when they put clocks in satellites and they send them up there was they found out that when the clock gets up there out in the region where it is not feeling the fabric of the universe being stretched, the clock runs faster. And so if they were to launch a GPS satellite And if they didn't use this equation that you see right here in order to adjust the calibration of that clock, then every day that goes by, the clock would be a little bit more and more and more in error, and your GPS would not work, because that tiny bit of error, that's enough to screw up your GPS system, and you would not be able to accurately know your position. So this equation right here is the equation that they use to fix the calibration in the satellites. So even though we haven't derived the equation, we definitely have a lot of experimental evidence that shows that this equation does match the reality. Okay, so time dilation when you're in a high gravity field, that's another one of the weird things that happens as a result of general relativity. Okay, there's another weird effect, which is called gravitational lensing. And when I say lens, I mean very much like the kind of lenses that we were talking about. Where'd my glasses go? Okay, I don't have my glasses, but pretend I'm wearing glasses, right? So the lens in your glasses, okay, the way that it can focus the light, gravity can do the same thing, okay? If you have a region where you've got a highly massive object, and so the fabric of the universe is stretched really tightly here, and then the further you go out, the less stressed it is, and the further you go out, the less stressed. So this difference in the stress of the universe can bend light, just like the difference in the refractive index can. So we talked briefly a couple months ago when we were talking about light, we talked about the mirage effect, and I'm pretty sure I did it with all three of the classes, okay? So if you've ever been out on the hot day, especially when you're driving, on a hot afternoon when you're driving out in the desert, and you look out in the road in front of you, you will, if conditions are right, you will see a blue puddle in the road ahead of you. But you never reach it because the closer you get to it, the further out it stays away. Okay, so what's happening is that the light from the sky, the blue light from the sky, is coming in here. Yeah, Joshua hates when it happens. Yeah, me too. Okay, so the light comes in here and then it travels through a region where the air directly above the ground is hotter because, because the sun has been shining on the sand all day long, or the pavement of the road all day long. So the pavement of the road gets really hot. So the air immediately above it is a lot hotter than the air above that. So it goes from hot air to cool air. Well, hot air is less dense, therefore has a lower refractive index. And so as you go up, it's cooler air. So you get this light coming in here. The light travels through a region where it's lower refractive index here, higher refractive index up there, causes the light rays to bend. And so the light ray gets bent. It looks here as though the light ray is bouncing off of the surface of the road. That's not the case. That's just a problem with the illustration. It is not bouncing. It is getting refracted just like a lens. And so here's the person standing there, they look this way and they see blue light, and it appears to them as the blue light is coming from here, when in fact it's actually coming up from here. That's exactly what happens in this case here, okay? So this is like where the air is really hot. This is like and therefore it's not very dense. This is like where the air is really cold and therefore it is dense. That has a higher refractive index, okay? Only it's in this case, it's not air. It's the fabric of the universe being stretched more here than it is over here, okay? So the light comes in and you get the mirage effect. And so when you're here on Earth, you're looking at this star just the same way that this guy is looking at the blue light coming from there. So the guy here thinks that the blue light's coming from here, even though it's actually from here. Same thing is happening here. We look at this star and it looks to us as if the star is here, when in fact the star is actually over here. This again has been verified to be true. In fact, very soon after Einstein predicted this, there was a total eclipse of the sun that was scheduled to happen. And I don't remember if it was months away or years away, but there was enough time so that before the eclipse occurred, Okay, so the sun was not located over here. The sun was way over here. So in the nighttime, the scientists took pictures of this region of the space where they knew that when the eclipse occurred, that this region was going to be right next to the sun. So they took pictures of this region of the space, let's say 6 months before the eclipse occurred. So on the day of the eclipse, that the sun has now moved around, or actually it's the Earth that's moved. Okay, so now the sun is in the sky at the same time as this region of the space is, and so normally you would not be able to see these stars because the sun is out and the sky is bright. Okay, but on the day of the eclipse, so the moon comes, and right here where I've got my arrow, the moon comes in and it blocks out the sun, so you can see the stars in the daytime that you normally would not be able to see. And this star that they know is actually right here, when they took pictures, they found that it appeared to be over here. And the shift was exactly what Einstein had predicted. Okay, so this really cemented Einstein's reputation when this happened. That was a big deal, big news in space, big news in science. Okay, now there's a related thing that happens called gravitational lensing. So in the lower right of your screen right now, you're seeing a little smiley face type thing. So that you've got some galaxies here, and then you got this really weird circle-like thing on this side and over on the other side as well. And this is an actual photograph. This is not a drawing. This is an actual photograph. Okay, and it's happening. What you're seeing is gravitational lensing, and so over here you can see a diagram for what's happening. So the two galaxies that you're seeing right here, they are located in between us and yet another galaxy that's more distant behind them. The light from this other galaxy is coming out, and it's spreading out this way, and because of the gravitational lensing, it gets bent around, and so it comes back to Earth. So if we follow the line back, it looks like the light's coming from here, even though it's actually coming from here. Same with the light on the other side. Okay, and so that's why we see this funny circle effect around there, is because these two galaxies are acting as a gravitational lens, so that they're bending the light from yet another galaxy that's further behind them. So yet another experimental proof that general relativity is not just a theory, it is in fact real. Okay, moving on, yet another of the weird effects of general relativity. It's called gravitational redshift, or it could be blue shift, depending on which way you're going. So if you are standing on the surface of the sun, which I do not recommend, safety tip, don't actually do that. Okay, don't try this at home. But if you could somehow stand on the surface of a sun and you have a red flashlight, okay, and you point it up, or let's say it's a blue flashlight. That works better because the picture here is blue. Let's say you have a blue flashlight, okay? You point it up. Well, that blue flashlight has to fight against the pull of gravity, because as we've seen, gravity can affect light. Even though light has no mass, it can still affect it. So that light, when it leaves our flashlight, it may start out as blue, but it gets red shifted the further out it goes. So it starts out as blue, gets changed to green, from that gets changed to yellow, orange, and after a while, it ends up as being red. And in fact, it keeps on going to infrared, and then microwave, and then radio. And in an extreme case, if you've got enough mass packed into a small enough space, that light can get redshifted so much that all of its energy gets used up and it cannot escape. So then what we have is called a black hole. All right, so this is an artist rendering of a black hole. Now some of you are saying, well, where's all this light coming from if it's a black hole? This light is not coming from the black hole. The light is coming from the matter that is being sucked into the black hole. Okay, so if I've got some piece of dust that, yes, quasars are similar. Yeah, But let's not go there. Okay, so I've got a piece of dust that's moving along this direction. So if this black hole wasn't here, this piece of dust would just travel over here and keep on going. Okay, but it's caught by the black hole, and so it's going to get pulled in. But it's not going to, well, it could just get pulled right straight in, but most of the time what happens is that it spirals in, okay? And it goes faster and faster and faster as it's spiraling around and around and around, and it starts radiating, okay, because you've got an electric charge that's accelerating, okay? And so all of this light that you're seeing is not coming from the black hole. It's coming from the stuff that is being pulled into the black hole, okay? So the black hole is causing it, but it's not coming from the black hole. Okay, so a black hole is basically just an extreme case of gravitational redshift. Now, the redshift and blue shift could work both ways. Let's say that you're a spaceman or spacewoman, and you've got a flashlight and you shine it to your friend on Earth. And let's say that let's say it's a green flashlight. Okay, so as this green light travels towards Earth, because of the gravitational effect, it's going to pick up energy as it goes. And so it's going to get shifted to the higher end of the frequency spectrum, which is the opposite of redshift. It's going to be blue shift. So it's possible that you could shine your green flashlight at a friend who's on the surface of the sun, and your friend is not going to see it as green. Your friend is going to see it as blue, or could be ultraviolet. Or maybe it's a red flashlight at the beginning, and by the time your friend sees it, it's green. So it doesn't have to go all the way to blue to be called blue shift. All right. Now here is yet another of the weird effects of gravity and general relativity. Now that we know that mass is actually a distortion in the fabric of the universe, if you can take a bit of mass and figure out some way to make it move, to make the mass wiggle in some weird way, that mass is going to send ripples out in the fabric of the universe. Now, because gravity is so weak, you're not going to notice this unless you can figure out some way to get two really, really massive objects to interact. And so what you're seeing here is like two black holes. And so the black holes are orbiting each other. And because they have so much mass, they're sending out all these ripples. And up until just a very few years ago, and I forget how many years ago it was, I think it was like about 2 years ago, people had predicted gravity waves. But because gravity was such an incredibly weak field, we didn't have sensors that were sensitive enough to where they could actually detect it. But about approximately 2 years ago, plus or minus a little bit, don't quote me exactly, some scientists figured out a way to build an incredibly super sensitive detector, and they set it up, and sure enough, they were able to detect gravity waves, and then when they looked at the nature of the gravity waves and they analyzed it and did the math, they're pretty sure that the waves are caused because somewhere off in the distance, there are two black holes that are gravitationally bound to each other and that are going around like a binary star would. And so gravity waves have now been experimentally verified to be true. Up until 2 years ago, it was just an unproven theory, but it has now been verified. Okay, well, here's yet another example. Okay, so you guys hopefully remember several months ago when we were first learning about satellites and orbital motion. Okay, we said that, okay, so here is the Earth, and we said here's the moon, and the moon is going around the Earth, or maybe it's an artificial satellite, doesn't matter. Something is orbiting the Earth. And we calculated all of the, the distances and the speeds, and we did a lot of math involving these satellites as they go around the Earth. Think back. At any time when we were doing that math, Did we ever worry about whether or not the Earth was rotating? Well, the answer is no, we did not. All of the mathematics that we did, we could not have cared less whether the Earth was sitting still or if the Earth was rotating, because we were still going with the old-fashioned model. We were still treating matter as if matter is made up of little marbles that are floating in empty space. So if it's true that matter is an empty marble floating in empty space, then whether or not the matter is rotating is completely irrelevant. But now we know that that's not the case. Now we know that matter is actually part of the fabric of the universe. And so if the Earth is rotating, like in the lower part of your screen here, okay, this is a picture of the Earth and it's rotating and it is connected to the fabric of the universe. It is part of the fabric. Earth is just a ripple in the fabric is all it is. Okay, so if the Earth is rotating, does it not make sense that it would pull the fabric, it would drag the fabric along with it? Well, yeah, it does. Okay, so Einstein and others, they said, okay, well, if that's the case, then if you've got an artificial satellite and it's in what we call a polar orbit, so it's going around the Earth and it passes over the South Pole, comes up, passes over the North Pole, back again. So if the Earth is rotating at the same time that this satellite is going from north to south, and the fabric of the universe is being pulled west to east, does it not make sense that the orbit of that satellite would be affected by that? And it turns out that it is. Okay. Now the amount is really small. If you look here on the screen here, and it's called frame dragging is what it's called, gravitational reference frame. Okay. You'll find out that it's an incredibly small amount. Okay, let's see. That'd be 1/10 of a degree, 1/100th, 1/1000th, I'm sorry, let's try again. 10, 100, 1,000, 10,000th. So that's about, we get down to about 1/100,000th of a degree per year. That's what the effect was predicted to be. And in fact, when they look at actual satellites, if you look at it with sensitive enough equipment, you have to have super sensitive equipment. But if your equipment is sensitive enough, you will find out that the satellite is in fact dragged to the side. Frame dragging is again something that has been verified experimentally to be true. Okay, and I think this is the last one on my list here. Okay, so again, if you think back several months ago when we were calculating the orbit of the planets, and we said, okay, the planets, you can do the mathematics if they're circles, but in fact they're actually ellipses, right? So we always assumed that when the planet goes around the sun, it comes back out again, and it keeps on the same path. What you see here looks like it was drawn by a spirograph toy. Did any of you guys ever have a toy called a spirograph where you got a bunch of little gears and some of the gears have holes in them? Yeah, okay, some of you have done it, good. So you take your pen, okay, and you stick your pen through one of the holes in the gears, and then you move them around, which causes this pen to make really cool effects. So you get this spirograph type effect. Well, that is actually what happens. And it's because of the gravitational effect. And this is called gravitational precession. So when a planet goes around the sun and it comes back out on the other side, it doesn't actually come out exactly on the same path that it was before. Passing close to the sun here causes it to get shifted ever so slightly, just like a light ray gets shifted. I mean, if gravity can bend the path of a light ray, well then for sure it can bend the path of matter, right? And so what happens is when it comes out the other side, it's going to be a little bit off. And so it's going to follow this second path. And when it comes out the third time, it's going to be a little bit off again. So it's going to cover out the third path. Okay. Now, remember with gravitational frame dragging, the effect here is super, super small. It's like 1/100,000th of a degree per year. Well, this gravitational precession effect is even smaller than that. Okay, because none of the planets really get close enough to the sun to where this effect really becomes very noticeable. But if you look at the planet that is the closest to the sun, which is of course Mercury, okay, you would expect that Mercury would be the planet that would be most affected by this. And in fact, when scientists look at Mercury's orbit, they find that it is in fact precessing at a rate that they can measure. Now, if you look at Venus and Earth, the amount of orbital precession is so small that we don't have instruments that are sensitive enough to measure it for Venus or Earth or any of the other planets. But for Mercury, we do. Okay, our equipment is sensitive enough because Mercury is that much closer, and so it is more affected. And so scientists have compared Einstein's predictions with the measurements that they've made, and no surprise, the measurements match the prediction. So general relativity may seem weird, to say the least, but experimental evidence has shown that it's real. Okay. All right, so here is a list of all of the general relativity weirdness. Okay, so I would recommend that you write this down, put this on your cheat sheet, because you never know. One of the questions on the test might be to list the weirdness that happens. Okay, so all the items that you see here are things that you need to know about, and you need to know what they are. So like, for instance, one thing I might ask on the test is I might say, what is gravitational frame dragging? And then you need to explain in words what gravitational frame dragging is. Or I might say, what is gravitational lensing, or any of the things that you see here on the screen. Those are things that I could conceivably ask. All right. Are there any questions? Not seeing any questions. Okay, so I'm going to move on. If you have a question, go ahead and type it in. Okay, now I'm going to put a handout on Canvas. I haven't done it yet, but during the next hour, while I'm waiting for Zoom to process the video, I will go ahead and I will put a page on Canvas where there will be a handout very similar to the one that I gave you last time. And basically it's another copy out of the same book. And it talks about general relativity. It doesn't go into as much detail as I've just done for some of these things. It just kind of mentions them in passing. So I think your best source of information for your homework tonight is going to be the video, which is being recorded. Okay. Now there are two things that the handout is going to talk about that I have purposely not talked about because I figured we wouldn't have enough time, and I see that I figured correctly. We've only got about 7 minutes left before it's 2 o'clock. So in the handout, they're going to talk about something that they call the correspondence principle and something that's called the equivalence principle. Now these two names aren't really the most descriptive names in the world. Correspondence and equivalence are two words that kind of sort of mean the same thing. And so because of the unfortunate choice of words here, a lot of people think that the correspondence principle and the equivalence principle are really the same thing, but they are in fact different. And so you need to read the handout. I'm not going to tell you here. I'm going to require you to read the handout. And I need you to make sure that you understand what is the correspondence principle, what is the equivalence principle, and I need you to realize they are not the same thing. And so be careful that you don't get the two of them confused. So pay attention to that. Okay, so speaking of tonight's homework, okay, so I'm going to need you to download the handout from Canvas, which I have not yet put on Canvas, but within the next hour, it will appear on Canvas. And then these are the problems that I want you to do, okay? And they're not going to be really calculation problems. They're all going to be just qualitative, you know, describe this or describe that type of problems. So I apologize for giving you homework on a Friday, but you know, I kind of had to, seeing as how I was given the command that I'm not allowed to give you any new material after today. So we had to kind of squeeze this in for today. So yes, Yazin, you do have homework today. I never promised that I wouldn't give you homework on Friday. I just told you that I would try to not give you homework on Friday, but it didn't work out that way today. Okay, so are there any questions? Now, while I'm apologizing, let me also apologize for the fact that there's a bunch of other really cool stuff that under normal circumstances we would have talked about. Like for instance, you guys know that a proton and an electron are not actually the smallest bits of matter. There are actually things smaller than them. I'm sure you've heard about quarks and leptons and hadrons and all that great stuff, okay? Well, if it weren't for the coronavirus, we would have learned about quarks and leptons and hadrons and bosons and string theory and up quarks and down quarks and charm quarks and strange quarks and yeah, all that good stuff. So how about let's make that be the secret word for today. You guys okay with that? Okay, so here is the secret word for today. The secret word is quark. And if you have some free time and you guys are bored, I would recommend that you Google quark and see what it is. I think it's fascinating. All right, so that's going to be the secret word for today. Cohen is asking, does the textbook cover that decently well? Yeah, kind of, sort of. It is talked about in the textbook. So if you're interested, I definitely do recommend it. I don't remember offhand which chapter it is, but if you get out the index and look it in there, they do have an entire chapter that's dedicated to subatomic physics, and I think it's fascinating. I hope that you guys would too. All right, well, looks like time is up, and I'm not seeing any questions. I'll give you just a few more seconds to hurriedly type a question if you have one. Okay, not seeing anything. Okay, it's time for the countdown. Oh, okay, there's a question. Okay, so Jaron is saying, are black holes spinning? And the answer to that question is yes, black holes are spinning, and they spin very fast. And we could spend a lot of time talking about that and talking about why they're spinning. But yeah, definitely they are. Okay, so Sarah wants to know, could I show the slide with the tests and the dates? Okay, yeah, that's an excellent thing to do. Okay, so boy, a lot of slides. Okay, there we go. Okay, so this is the schedule for next week. So those of you who joined us late. Okay, so the plan is on Monday, we're going to go over the answers to the homework tests, or the answers to the homework problems. And I'm going to give out the practice test. On Wednesday, we're going to spend the whole day going over the answers to the practice tests. And on Friday, we're not going to hold class. And then on Monday, the 18th, that's when the real test will be. Okay, so Bridget wants to know if you need to know the order of the weirdness effects. And the answer to that is no. There really isn't any order. I just kind of put them at random order when I put them on there. So yeah, don't worry about knowing the order. Okay, so I'll start the countdown again. Going once. Oh, okay, Yazin wants to know if you can keep your books. Okay, so Yazin, the answer to that is, if you have one of the newer books, one of the books that's in good condition, one of the books where you signed it out and you wrote down the book number, then the answer is no, you cannot keep that book, I need it back. If, on the other hand, you're one of those people who took one of the really lousy books, the one that's all really chewed up and it was in bad condition, and so it was in so bad a condition that I told you, hey, don't even bother signing it out. Just take it, and then if you don't bring it back, excuse me, and if you don't bring it back, I won't care. So if you have one of those books, then you don't need to bring it back. Now, what I will say is that if you are not planning on using it, it would be nice to bring it back, but because next year somebody else might want it, right? So it'd be nice to bring it back, but not required. Okay, so Annie wants to know if you can borrow the books over the summer and give them back next year. The answer to that will be yes. I will be okay with that. Now, what's going to happen is Nancy Carpenter in the office, she's keeping a list of the, we call it the naughty list, or sometimes we call it the fine list. So if you have one of the new books, one of the books that's in good condition, and if you want to keep it over the summer, please send me an email telling me that you want to do that. And so once I get that email, I will then send a note to Nancy telling her not to put you on the naughty list. Okay. All right. Here we go for our third try. Let's see if we can make this time. Going once. Going twice. Sold. Goodbye, recording people.